This program is a presentation of UCTV for educational and non-commercial use only.
I want to welcome everyone to Livermore and to the Bankhead Theater. The community of Livermore is delighted to have this new theater so that we can offer an event such as Science on Saturdays. Also, a special thanks goes to the Lawrence Livermore National Lab for providing this science series for students and their parents. The partnership of the lab and educators in our area is a wonderful example of the support that good neighbors give each other. Today's topic is aerogels, whatever that is. I'm a word person, so I started by trying to figure it out by taking the word apart. Aero, of course, refers to the air, the stuff around us that seems to be a whole bunch of nothing. But we do know that air contains oxygen, at least some, which we need to live. And it also contains the carbon dioxide that we contribute every time we exhale. So much for aero. Everyone is also familiar with gels, like Jell-O. It starts as a liquid. You add the powder in the envelope and mix, cool it, and soon it becomes solid. Not frozen like ice, but it has gelled. But I'm having a very difficult time connecting the nothing of air and Jell-O. Our presenters this morning will unravel this puzzle. Alex Gash grew up in Reading. In high school and college, he was a football player. He earned his bachelor's degree at UC Davis, then worked in agricultural and mining industries, mostly on soil and minerals. Then a PhD from Colorado State. He came to the lab studying a wide range of materials from heavy metal absorbents to nanocomposites to ceramics. Since 1999, he's been a research chemist in the Advanced Materials Synthesis Group, Chemical Sciences Division, investigating low-density porous materials like aerogels with an eye to their abilities in energy storage. Dean Reese, also a part of the presentation team, teaches physics and biology at Tracy High School. He grew up near Plymouth, Massachusetts, and was a multi-athlete in high school. He majored in astronomy and physics, a double major at the University of Massachusetts. Came to California to teach in Tracy. Now he's also working on a master's in science education from Western Governors University. He was also in the United States Army National Guard. And now, to give us the whole story, aerogels, the materials science of empty space, please welcome Dr. Alex Gash and Dean Reese.
Hi, my name is Alex Gash. I'm a materials chemist at Lawrence Livermore National Laboratory in Livermore, California. Today's Quest Lab is all about aerogel, the lightest and lowest density solid on the planet. This material on the inside is made up of very small nanometer-sized particles of silicon dioxide that are interconnected in a porous network. Lots and lots of very small pores. In fact, if you were to take 1 gram of this material, flatten out all of its nanostructure and expose its surface area, it would cover an area the size of a football field. For its density, aerogel is incredibly strong. Aerogel can hold, in compression, up to 4,000 times its weight in force. Even though it's got this good compressive strength, it is very brittle. One of its best properties is its thermal insulation. The excellent thermal conductivity properties of the aerogel are because of its unique structure. That tortuous, porous path that I showed makes it very difficult for there to be heat conduction either through the solid or through gas from one side of the aerogel to another. Although aerogels have been known since the 1930s, it's really only been in the last 20 years that we've been able to look at some real interesting applications of this material. Aerogel may someday be used by NASA to insulate spacecraft, and potentially one day it could be used to insulate your home. From Lawrence Livermore National Laboratory, I'm Alex Gash. Thanks for joining us on this Quest Lab. All right, good morning. So I'm Alex Gash, and I'd like to thank all of you for coming up here this morning to listen to our presentation here. Before I get started, I want to acknowledge my co-author and co-presenter here, Mr. Dean Reese from Tracy High School. So the title of the talk is Aerogels, the Material Science of Empty Space. And aerogels are, to coin the phrase, a whole lot about nothing. Hopefully it's not. Hopefully by the end of this, you guys don't believe that. But, excuse me. All right. So what are we going to talk about today? The points we're going to hit today. First of all, I'm a chemist. I'm a materials chemist. So before we get too much into the science topic here, I'm going to talk a little bit about the diversity of careers that are available in the chemical sciences, because, like I said, I'm a chemist, and I enjoy my job, and I'm always looking to recruit new people to be chemists. Then we're going to get into talking about what an aerogel is, and specifically what it's made up of, how it looks like on the outside, how it looks like on the inside. I think you're going to find it's a very unique material that you may not be very familiar with, but it has some attributes that you can relate to. Then actually we're going to do a demonstration where we actually do the first two steps in making an aerogel. And then we're going to talk a bit about the physical properties of aerogels. And then talk about how they're used currently today and how they might be used in the future, and how Livermore is looking at them for future applications. So, like I mentioned, I have to give a plug for chemists here, as I'm a chemist. So chemists, this is what chemists look at. This is a periodic table. It has all the elements in it. Chemists study the property, the composition, assembly, and properties and reactivity of atoms in the periodic table that then combine to make molecules, which then can even combine to make extended solids and materials. One of the things that always attracted me about chemistry, even early on when I was more your guys' grade level, or the predominance of the audience, is that one of the things I like about it is it's very cross-cutting, and some people call it even the central science. And of course, I'm chemist-centric here. But the point there is that chemistry is at the boundary of all these different scientific disciplines: biology, materials science, medicine, astronomy, environmental science, geology, and physics. All of them incorporate aspects of chemistry. Chemistry is used in all of these, and I always found that very, very attractive, because these are all areas I'm interested in. Basically what I'm saying is that chemistry has a lot to offer based on what your interests are. If you'll indulge me, I have a couple more slides on what a chemist does, because you may have a conception what the stereotypical chemist, and certainly there are stereotypical chemists, the guy in the lab coat with partially frosted eyebrows from some reaction that went wrong or something like that. But there's other aspects of chemistry I want to talk about. I'll start though with there's a subset of chemists called synthetic chemists, and actually that's what I am. That's why I put it first. They're actually chemists that make compounds and materials. As a kid, I always liked making things, making materials, things I could hold, things I could look at, maybe under a microscope or something like that. So synthetic chemists, and this is very broad, they take chemicals, which are made up of atoms, and they try and rearrange them. So there's sort of, in my opinion, there's a little bit of an artistic and creative slant to being a synthetic chemist. You see this beautiful caged molecule here. And study the properties of these, and many of these things can be very useful. And so synthetic chemists make plastics, they make metals, make all the materials that make up components in a variety of different technologies. One of the large areas is the pharmaceutical industry. You get a large number of synthetic chemists work in that industry, making new drugs to treat disease and ailments throughout the world. There's another type of chemist that you might be a little more familiar with for those of you that are familiar with, for example, CSI, all the CSI series, and that's what I'd call an analytical chemist. So an analytical chemist actually measures the properties of materials, looks at the signature of materials. There's a little bit of sleuthing to it, a little bit of like crime scene investigators. Analytical chemists are very important. They measure purity of materials. They can be involved in law, for example, law enforcement or even treaty enforcement, where they look at chemical signatures of events that have happened and try and work with investigators to find out the true story behind it. So that's an attractive area of chemistry. The last one I'm going to touch on is actually computational chemists. And this is actually an area that these people are definitely not the stereotypical chemists. With the development of computing, especially massively parallel supercomputer systems like the Blue Gene L that we have out at Livermore Lab, you can now chemists can actually sit in their office with the right programs, and they can actually predict whether, and they can model, chemical reactions and potentially material structures. And actually, it's very valuable to have a computational chemist working with a synthetic chemist, because lots of times a synthetic chemist may have a lot of ideas about things to try, but the computational chemist can give them some kind of idea what they believe might work better. I mean, complex problems like, with large supercomputers, you can look at complex problems like protein folding, which is very important to the fields of biology and medicine. Anyway, this is a very fast-growing area of chemical science because we get a lot of younger people interested in it because they've grown up using computers, they've grown up using electronics, they relate to it. And so while we'll always need synthetic chemists, I just want to make sure people realize that there are careers for all interests in chemistry. So what does it take to become a chemist? Clearly, you need a strong interest in science as well as a strong performance in science. College degree, four-year college degree there, a bachelor's degree in chemistry is actually, one of the things that always attracts me about chemistry is with a four-year degree, you can actually do a fair number of things in chemistry. Chemists are very employable. Then you can go on to graduate school, for example. You can talking about 2 to 4 years of graduate school. And there are any number of fine graduate institutions in the U.S., on other continents, Europe and Asia. One of the things I like about it, I think it's a really diverse and rewarding career, where I'll put my own plug in there. I like the creativity of it, especially creating new materials or modifications of them. Chemists are everywhere. Chemists work everywhere. It's a worldwide industry. So if you have interest in working in other countries or something like that, that's another good path or possible career track here. And probably the most important thing from my aspect is that you get to work on really important global problems. Many chemists are interested in, chemists contribute to solutions to energy issues, or they will contribute to energy issues and how we might solve them in the future, as well as pollution issues and the eradication of disease throughout the world. So now that I've given my talk on chemists and what they do, and I'll stop with that, let's talk about the scientific topic today, and that's aerogel. So as Anne pointed out, an aerogel, she broke it down, and that's a really nice way to start. You could almost call it an air solid, okay, or an air where in the gel here you might be familiar with Jell-O or hair gel, for example. In gels, you got a part solid and part liquid, okay? In this case, instead of having liquid, what we have is part solid and part air. And this right here is a silicon, this large one. These are a number of aerogels laid on top of one another. And so there were some questions in the last period. We can actually we're going to talk largely about silicon dioxide aerogel materials, but you can make them with other elements in the periodic table. Anyway, we'll go back to silicon dioxide. So the aerogels we're going to talk about and make today are made up of silicon dioxide. Well, what is silicon dioxide? Silicon dioxide is actually the same composition, has the same elemental composition as sand. And Mr. Reese over there is holding up a vial of just beach sand. Now, you're all familiar with beach sand. It's something you can relate to. You have the grains, right? You put them on your fingers. You look at and those are the little particles, right? But you can see them with your eye. Now, you also, in an aerogel, you can take a grain of sand, now reduce it by about 30,000 times, way down small. And those are the little particles that make up an aerogel. And like I said, they're essentially the same chemical composition as sand, but they're put together very differently. Also different than sand is that the aerogel is fused. All those particles are connected in some way or another to make a solid, rigid structure. So it has very small particles and very small pores. And when I mean pores is, let's go back to the sand analogy. You've got a cup of sand. You know that you could pour water in there, and the water would take up some of that volume, because in between the grains there's a little bit of space. Well, there's the same little bit of space in aerogels, but you can imagine now that the size of the particles has gotten much smaller, those pores have gotten much smaller. And actually, there's a picture. So this is a high-resolution electron microscope image of an aerogel, and it's on a very small scale. That's a 50 nanometer scale bar. We'll talk about a nanometer in a moment. But you can see it is mostly air. Look, it's a Swiss cheese. It's a network of particles that are fused together with a lot of open space in between. One of the things I think is especially interesting about aerogels is they are nanomaterials. And I'll talk a bit about nano in a second, but you can actually pick them up with your hand. So nano, you guys may have heard of nano, use that prefix before. And it's very common, nanotechnology, nanomaterials, it may be something you've heard. But let's talk a little bit about what nano means, actually, and it all has to do with length. So I'll start with something a little more related to pop culture. Read this right here. What's this? This is the iPod Nano, right? And so what's the difference between the iPod Nano and the regular iPod? Well, the first thing, it's smaller, right? It relates to size, and so nano is the prefix for nanometer, and so nanometer is a metric unit of length. Okay, it's like a centimeter or same as a centimeter or a meter, that it's a length, but it's a very small unit of length. Actually, it's 1/1000th of a meter. So 10 to the minus 9 meters are the size. Here's another image of nanoparticles. You can see these are like 10 nanometer sized particles, so extremely small. And why there is a lot of interest in nanomaterials is nanomaterials behave differently than materials in bulk. And one of the reasons they behave differently is that you can think of a nanomaterial, a lot of that material, a huge percentage is on the surface. And to a chemist, surfaces are great, because surfaces are where reactions take place. That's where you get adsorption, desorption, you get catalysis. So from a chemist standpoint, aerogels are really interesting materials because of all the surface they have. So something else you can relate to a bit is the material properties. And the aerogel is listed no less than 15 times in the 2009 Guinness Book of World Records. And we're not going to talk about all the different extreme properties. But it is the lowest density solid recorded. It also has the lowest thermal conductivity. That means it's really good at retarding heat transfer. And also one of the highest surface area solids. So I'm going to actually do a demonstration here now. I have to go over it and mix some chemicals together, but we're going to talk about how we actually make it. And we make aerogels using something called sol gel chemistry. And there's a couple, we talked about gel, but let's talk about sol here for a second. So a sol is a suspension of very tiny solid particles in a liquid. So small, actually, you really can't see them with the naked eye. And they're so small, actually, they really aren't influenced by gravity. Actually, you guys deal with sol every day. Milk is actually a sol. Milk is mostly water, but it's got tiny little particles of lipids, proteins, and fats that are suspended in it. That's why it's opaque. And so you guys deal with sols every day. A gel, again, to reiterate here, is a solid network of particles that contains pores filled with a liquid. An example here is Jell-O. Jell-O is a gel. It's something we can all relate to. So I'm going to go through over here. I've got to step over here and put on my correct stereotypical chemist stuff. But I'm going to actually make a gel here. I'm going to mix two chemicals here. You have the precursors in it to make silicon dioxide gel. Let me get my gloves on. So what I'm doing here, one of these, it's a solvent. Most of this is ethanol. And it's got a silicate precursor in it. So I pour that in to my Erlenmeyer flask here. And now we could let that sit there and nothing would happen. But I'm going to add the second reagent, which actually contains a catalyst as well as a little bit of water, which helps hydrolyze and cross-link these materials. Now I figured this out so it would take about a minute to gel. So you can see right now it's still a liquid. Good, we're getting a good view of it here. And I'll swirl it to show you that it is in fact a liquid. And in a moment here, you're going to start to see. So right now, we're at the initial phases. We're actually growing a sol. Believe me, we are. You can't see it. But pretty soon you're going to see this start to change a bit. It's become a little opaque because those solid particles are now growing, and they're growing big enough that the light is starting to scatter them. And I'm going to set this down here for a second. Still have a view of it. Actually, maybe I'll lift it up. So this, and it's warming a slight amount. So what happens is that sol grows, and it'll grow if it grows to a certain point, and we can arrest it, and it'll just be a solid in a liquid, so it'll still continue to be a liquid. But if those particles continue to grow, they actually then start attaching to one another, and they make spaghetti strands or strings of pearls. You'll see some of the cartoons I have here. And it'll firm up to a gel, and a gel is just, for here, it's a rigid structure, and it spans your container. So you can imagine this is real amenable to making molds. You can make all different types of shapes. You can see up here we've got cylinders, we've got a sphere, that type of thing. But it becomes a gel, and it becomes a rigid gel. And if I've done this right, when I turn it, nothing's going to spill on my hand. And there we go. So we made a gel. And these are essentially the first two steps in making an aerogel, is to form the sol, which we did, and then cross-link the sol. And I knew how to do that based on experiments we've done in the past. I knew what types of chemicals we needed to add. So, as you can imagine, I got excited here because I just got to make a material in front of everybody. But it may not have been that exciting for you. Let's talk about what we do after we make the gel, how you get from a sol or something like that to actually a part like this, okay? So I've got this animation here. I'll summarize it quickly, but we formed the sol. Remember, we grew the sol. And then the sol cross-linked to form the gel. And that's what basically you saw there. So, and you saw the demonstration here. So, like I mentioned, there's really three steps in making an aerogel. The sol formation, which you watched me do, the gel formation, and then the drying, okay? And the drying is tricky because the way you dry it basically determines whether it's an aerogel or something called a zero gel. If I just took that and left that out here, and we left it here in the Bankhead Theater for a couple days without putting the ethanol would all evaporate off, and what happens is the gel would actually shrink down. It would collapse because there's very little solid material in there. And one of the reasons, the reason it would collapse is because when it evaporates, you get these stresses in the material, and it shrinks on it. But you can dry a different way using supercritical solvent. And in a solvent in its supercritical state, it doesn't exert forces on the gel when you evaporate it. And that's how you make an aerogel, is you supercritically dry. That's the critical step there to make an aerogel. Now, adults in the audience might know that actually they use supercritical fluid, supercritical carbon dioxide. That's how they decaffeinate coffee. They wash it in supercritical solvent. So now we've talked about making a gel and gone through the steps. I'm going to now talk about the concepts of density. Mr. Reese and I are going to talk about the concepts of density, mass, and volume. So what we've got here is, let's talk about mass. So mass, let's simply say mass is how much something weighs. So you've got something in the Earth's gravitational field, in the Earth's gravitational field, and you want to know what the weight of it is. That's essentially the mass. And so right here I've got a bar of gold. That's something you can relate to, big bar of gold you might see. So it has a mass. We put it on a scale. We know how much it weighs. Just to give you an idea of how mass increases, say like we had an identical cube or identical bar of gold, all right? And we put them together on that scale. Well, they'd weigh twice as much as one bar of gold, right? So now that's mass. So then let's talk about volume, which is essentially the amount of space that an object occupies. So you've got, let's say this is just a shipping box here. As you know, everything that's in that box, that's the volume it's contained in. That's the space it takes up. And Mr. Reese has got another demonstration here to sort of get this point across. Here.
Okay. I like audience participation, so if I ask you questions, just feel free to shout out answers. That just makes it more fun. So what we have here is one of these cool toys that you've probably seen before. You can kind of like pull it and watch the shape expand and take up more space. But let me ask you this. When it's like this and when it's like this, has the mass changed? Right, so the mass is staying constant the whole time, but if we kind of take all that mass and squeeze it into this little space, the volume's small now. So you got a lot of mass and a little bit of volume. And so do you think you have high density or low density? Yeah, you guys got it. Okay. Then if I were to pull this apart, now you get the same mass, but in 3 or 4 times as much space. So now the density is obviously much lower. That's right. So that's the idea of density. You guys got it.
Well, since you guys got that so well, I can just skip through the next slide. But before I do, actually, just to reiterate what Mr. Reese said. So density, and the reason we're focusing on this is because we're going to talk about the material properties of the aerogel, and a lot of them are related to its low density. So I want to make sure you get the concept of the low density. So essentially density, we talked about mass and volume. Density is just that ratio, mass divided by volume. You might want to look at your questions here because I think there's a question in here that relates to this. So we can relate to materials that are high density. So those are materials that have a high mass in a small volume. So what are some high density materials? Well, lead, gold, heavy metals, steel. They're very heavy for the amount of space they take up. For low density materials, an example here, I'll put aerogel because that's what the topic is. And a nice analogy is, it's like a box right here, right? You see the empty box in your garage, right? You go to pick it up, it's big, you're expecting it to be heavy. You lift it up, all of a sudden, whoa, it's not heavy, it's empty. So there's a lot of empty space in there which keeps its density low. So low, actually, aerogel, so that's the concept of density. Now let's take it to an extreme, and that's what we're doing with aerogel here. This is actually, it's the lowest density solid known. The density aerogel can be 1,000 times less than that of water. So actually it can be 1 milligram per cubic centimeter. And we've got some 1 milligram per cubic centimeter you'll see in a demonstration a little later. It's in this little glass container here, but you couldn't see it if I was in the picture. We're shining a laser through it, and the laser's scattering the light, and that's the only reason you can see it. So we'll to further illustrate the low density of aerogels, Mr. Reese is going to do a demonstration with a balance here and some aerogel.
Okay. So we have a scale here, and what do you think this scale is supposed to measure? It's like a balance. So what do balances usually measure? Yeah, weight or mass, kind of like the same thing, right? So we got a chunk of aerogel sitting in this left cup, or maybe you're right? And I have popcorn here, and you all know how light popcorn is. I mean, I have like just 6 kernels in my hand, and if I start filling up the other tin with the popcorn, eventually you'll see that the balance kind of levels off. And that's literally how light this stuff is. It's so light. And look how much space it's taken up, and it's as light as 6 pieces of popcorn. So imagine how low density aerogel is. Pretty low.
We talked a little bit, introduced aerogels, and we made one. But now we want to talk a little more about, now we have a dry gel. Let's talk about what it looks like on the outside and the inside. Because what's on the inside is really important to the extreme properties that it displays. So here's a monolith. We'll call it a monolith, standalone monolith of aerogel, like those over in front of Mr. Reese. So if I just look at a little section of that, in a fairly high-powered electron microscope, you can see it's granular, okay? It's a little fuzzy here, but you can see there's particles and there's pores, right? These black things, these are the empty space between particles. But if then I focus in with even a more powerful electron microscope at one of these little particles, even that particle is made up of a bunch of smaller particles in a porous network. So it's got primary particles that make up these secondary particles that then glue together. So what this provides for the chemist is a massive amount of surface area. And 1 gram of this material can have up to 1,500 square meters of surface area. And like I said, chemists are interested in surfaces because that's where all the action happens. And that's where everything is where you get interesting reactions to occur. So I'm going to talk a little bit about what I mean by surface area and why it's important and relate it to an actual application, a future application that you guys should have a lot of interest in. But before I get that, I want to talk a bit about surface area. So this is the idea of surface area. We have a cube here, say for example of salt or something like that. And if you measure the area of the sides, and there are 6 sides to this cube, we can only see 3 of them, and you add them all together, that's the surface area, you know. Just think of, you know, the area of your room or something like that. So height times width, and then added. Now let's say, for example, I had a really fine razor blade, and I split this guy in half. I split it in half. Has the surface area changed? It has, right? Because I have new surfaces I exposed, right? That face and then the face you can't see there weren't exposed here. So it's something on the surface that a gas or liquid could absorb onto. Now let's go again. Let's slice this way. Again, now there's more surface area. I've opened up more surfaces. Now let's get a little crazy here. Let's get really, really small razor blades and just chop these things up. Now your surface area goes up. And so your surface area increases as your particle size decreases. So now we'll go back to the aerogel. Remember how small the little grains of silica are that are in there. They really have high surface area. And these types of materials can act like a sponge. So Mr. Reese and I, to illustrate it a little better, are going to do a demonstration here on surface area.
So we want to show you how much surface area is trapped in this tiny little piece of aerogel. So you can kind of see it better if I take this laser and scatter some light inside of it. You can kind of, I mean, we're talking about a very small little sample of aerogel. But remember, this aerogel is made up of nanoparticles. It's kind of like taking that box that we had up here and splitting it up and splitting it up and splitting it up, you know, several times, like, you know, many, many, many times until all you have is little tiny pieces. And we were talking how the surface area will start to increase as the particles get smaller. And we want to show you just how much surface area is trapped inside that little piece of aerogel. So we actually made this piece of paper. Here.
So that little piece, like Mr. Reese was saying, that little piece of aerogel has 5 square meters of surface area. And just to demonstrate that, Mr. Reese put together this piece of paper that's 5 square meters.
It's kind of big.
So there's that much surface in that little part we had. So this is 1 meter by 5 meters. And just wanted to illustrate to you guys. Now you can imagine, you know, that's a gram of it is of the highest surface area materials, 1,500 square meters. I mean, we wouldn't be able to get that in here, so that's why we did the 5 meters squared.
So,
yeah. So now we've given a demonstration on surface area, but why is surface area important? Like I mentioned, why might you guys think it's important? Well, let me relate it to a current technological challenge, and that's our energy source for the future. And you may have heard there's a lot of interest in hydrogen as a source for future energy, okay? And in a lot of ways, it's really a fantastic candidate. It's clean. We generate it from water. There's plenty of water around. Conceptually, you can use sunlight to hydrolyze it. That means take H2O, right? H2O is made up of hydrogen atoms, 2 hydrogen atoms and 1 oxygen atom. You can split them. You can form molecular hydrogen, molecular oxygen. You can store your hydrogen, okay? And then that can be burned, essentially. And one of the particular interests is in a hydrogen car, which there have been other Science on Saturday projects about. So in many ways, it's really a fantastic candidate. It's clean, it's renewable. You can pretty much do it anywhere where you've got sunlight and water. But like everything, you can say, well, geez, if it's so great, how come we're not using it? Because it has problems. And one of the problems here is how do we store it? And that's one of the areas where aerogel might be able to help. So one of the critical problems, and there are other ones, but how do we store it? Because gasoline, which are used in internal combustion engines now, is a liquid. And it's actually fairly dense. You know, it's a fairly good way to store energy as a liquid. And we burn it, right? Hydrogen's a gas. So now you're going to something that instead it's condensed, it's a gas. So it's really hard to get a lot of hydrogen because you need to compress it down into something reasonable. So typically gases get compressed into gas cylinders, right? So we've got a hydrogen car here, and look how small it is. But if we're going to put any reasonable amount of hydrogen on it, it's going to be difficult to stick a cylinder on there, or several cylinders on there, right? Because it's going to increase the weight of the car and sort of defeat the purpose we're doing the whole thing. So how might aerogels help? Well, one of the things they're good at, because they have high surface areas, and there are other issues too, but the main one is they're really good sorbents. And what I mean by a sorbent is it's a solid material that absorbs either a gas or a liquid, okay? And so these materials, actually they're carbon aerogels, not the silica. They're very good at absorbing molecular hydrogen and holding on to it at room temperature. So you don't have to pressurize it, you don't have to cool it down quite a bit. And there's currently a project going on at Livermore where we're looking at that. Looking at the different aerogel materials and how much hydrogen we can get into them. Hopefully this will go well. It's in this video here. So this is a video that just to explain the sorption of hydrogen. This is, again, our ball and stick cartoon figure of what the microstructure of an aerogel looks like. And you can see here that I've got this animation that just keeps cycling. These dumbbells are the diatomic hydrogen. They're small, they diffuse in, there's a lot of surface, so there's a lot of spots for them to sit. Rather than like one large cube where you couldn't cover very much, you've got all these little particles, and they can absorb a large amount of hydrogen. So this is maybe a potential material for solid hydrogen storage. So I'm going to shift gears a bit and talk a little bit about optical properties of the material, because that's something you notice right away. You know, if you look at the aerogel samples that are over there, one of the things is we can see through them to a certain degree. And so I want to talk a bit about how well we can see through them and some of the terms related to that. Since it's mostly air, it really appears to be transparent or translucent. But what do I mean by that? So it doesn't come out real well on the slide, but these terms, opaque, translucent, and transparent, refer to the optical properties of a material, the basic optical properties of the material. Each one of these cards has a star behind it. The opaque material, you can't see through at all. Nothing gets through. You can't see through it. So when you hear something like, oh, there was an opaque solid, that means in the solid you can't see through. Now translucent, this doesn't come out real well in here, the lighting in here. But translucent is you can see the faint images of the star. And you can imagine like frosted windows in a bathroom or something like that. That might be something you relate to at home, where you can see that there's somebody in there or there's something in there, but you can't really make out the features. And then, of course, there's transparent, which you can see through and read through and that type of thing. So Mr. Reese is going to do a demonstration now, and we're going to get some audience participation, and I'll let Dean take it over.
Okay. So we were talking about how you have three different types of optical properties. You have the opaque substances, can't see through. You have the translucent, which is kind of like foggy, kind of like wax paper maybe. And then you have the transparent, which is really easy to see through. And some aerogel up here, which one do you think that is? Do you think that's the opaque, the translucent, or the transparent? Yeah, that's the translucent. Good, because it's like you can see through it kind of, but it's not like if I had like a card back here with some letters that you could read those letters or anything like that. But it turns out, if you make the aerogel really low density, you can get the aerogel to be pretty transparent. In fact, I'm going to challenge you to try to see if you can guess which one of these boxes has aerogel inside of it. And I'm going to have you vote. So, if you like box A, maybe you're looking up there and you're like, you know what, box A kind of looks like it has aerogel. Then when I say box A, everyone's going to yell box A. But if you think box B has got to be the one with aerogel, then when I say box B, you, of course, are going to yell box B. And then, likewise for C, I think you get it. So, here we go. Who likes box A? Yell box A if you like box A. Box A. Okay. All right, not many people like box A. Okay, what about box B? Box B. Okay, a little bit better. What about box C? Box C. Does C? I don't know. Okay, they look the same to me. All right. I'm going to shine a laser through here, and I kind of tricked you a little bit, because there's actually two boxes. You can see box B and box C are scattering light, and box A doesn't, because box A doesn't have the aerogel. So it turns out if you voted box B or box C, you were right, which was most of you, so that's good.
Most people, yeah, good job.
Nice job.
You guys did better than the 9:30 crowd.
That's right.
A little more awake. So just a little background, those little cubes that he had, that actually has the 1 milligram per cc, the lowest density solid, are in those cubes. And you might ask why we use those cubes. Well, if we didn't use those cubes, we'd lose them, because they're very easy to lose because you have a tough time seeing them. You guys are better at seeing them than I was. So I'm going to transition now and talk a bit about one of the other, what I would call extreme properties of aerogel, and that is how well its thermal conductivity problem, or how well it resists heat transfer. So before that, though, we've got to talk a little about heat transfer and how you do heat transfer. And this is something you probably that's in your study guide. You may want to follow along closely here, particularly closely. So one thing we know is heat flows from regions of high temperature to low temperature. So you take your hand, there's a hot pan on the stove, put your hand on it, the hot transitions to the cold, which is your hand, you get a burn. So that's heat flow. But it can flow in several different ways, okay? And this cartoon of a campfire talks about that, how we get heats transferred by a campfire. So there's nominally 3 ways it's done. One is convection, which is heat transfer by fluid movement. And when we mean fluid, it could be a liquid, or fluid could also be a gas. So here, the cartoon figure there is warming his or her hands because of the convection currents heated from the fire here that heats up the gas there and drives it upwards. So that's convection. Another way you could get heat transfer here is conduction. So that is, let's take a solid iron rod and put it in a fireplace. And we know that if we grab that rod after a couple minutes, it's very warm. And that's conduction. That's heat transfer by solid conduction along the pathway there. And then finally, a little more esoteric is the fact that you can actually get heat transfer by radiation through electromagnetic waves. And it's maybe not as clear here, but I'll give you an example. Sunlight, right? Sunlight's coming in. It's electromagnetic waves in the visible UV spectrum. And we stand in the sun, we heat up, right? So that's another way heat can be transferred. So why are we talking about heat transfer? We're talking about heat transfer because maybe the most exceptional property of aerogels, and in the area where it seems to see the most use in applications, is that it's the best thermal insulator known. And so you can see these rather graphic demonstrations here of aerogel at person's hand at room temperature over the Bunsen burner. That's maybe 1400 degrees right there, and they're just feeling room temperature there, and that's only 1/4 of an inch. I would, if you did that with, let's say, a piece of metal, you would burn your hand. The only trick you saw in the video at the beginning, the scientist holding the aerogel with the flame over it, and he held it there for quite some time. The only trick there is the aerogel. You don't want the aerogel to crack, because if it does crack, then you will get flame that will shoot through, and you'll have a hot hand. So we're not doing the demonstration on thermal conductivity due to some technical difficulties, but I will talk about one of the ways, just one reason that aerogel is a really good thermal insulator and it has such low thermal conductivity. And it actually involves convection, which is directly related to the microstructure of the material. Again, we've got our cartoon here, and I've got flame here and a great big Frosty the Snow. I couldn't believe how big that snowman was when I found that picture. But anyway, so you've got hot side and a cold side here, right? And so convection, remember convection is heat transfer through fluid, right? So in this case, it's going to be a gas. So I've got a little animation here. This little red ball is a gas molecule. Now, in an aerogel, you've got very small particles and very small pores. And so the gas molecule heats up, it's got thermal energy, and it starts moving. And if it can get over here really fast, it's a poor thermal conductor. But one of the ways that it retards thermal conduction is through the fact that as we move this molecule through, it bounces off the small particles, and it can't go very far before it bounces into something else. So what happens is our gas has a tough time, our heated gas that would heat by convection has a tough time getting through, okay, because it's just a tortuous path. It's going backwards, forwards, it gains 2 steps, then goes back 3, and it never gets over to Frosty. Okay, so why is that important? So why is thermal conductivity, the low thermal conductivity? And there's other reasons why the thermal conductivity is really low, but that's the one. So again, going back to the energy problem, is energy efficiency is a really important path forward. All these alternative technologies like hydrogen and solar, they're important, but energy efficiency, making things more energy efficient, really will help also. And so low conductivity in like building materials really would help minimize heat loss and lower heating oil costs or lower heating costs that would make everyone here happy. And so here's an example of an old house that they remodeled, and it's in Massachusetts where Mr. Reese is from. And they remodeled it. There are some companies now that are making building materials out of aerogel, specifically thermal insulation.
So they insulated the top floor with something they call Insucap, which is an aerogel-based material. And then this, they did normal insulation. And then they took a thermal image of it, right? And the thermal image where it's lighter, that's where you have a lot of heat. And so you're looking at, this is a hot wall down here. So heat's radiating from inside the house out. And so that's poor efficiency. And you can look how how yellow it is on this lower one. Now let's go upstairs here, right? And now look, the thermal losses are much dramatically reduced with this insulation. So this is just one example of how it helps. Another is, look at these windows here, right? The windows are really the conduits for all they're really good thermal conductors, which is bad. And so I want to talk about how actually aerogels are used to solve a problem there. So light's scattered by aerogels, and the reason it's scattered is because we've got all these really small particles and pores. And we've got light, so here's the visible spectrum, and it's coming through, and there's different colors in the visible spectrum. We see that in rainbows and through prisms. And the lower wavelength, like the blue wavelength lights, they interact more with the particles and they scatter. And that's why aerogels always have sort of a blue tint to them. So, but still a great deal of light gets through, and so that actually makes them, one of the things they're used for extensively is for skylights in new architecture. So this is actually a school in Ohio that's got aerogel skylights, and in both the multi-purpose room and the library. And Mr. Reese has got a little mock-up we made of an aerogel window that he'll show you now.
Okay, so a good place to put aerogel, as you saw in the picture with the house in Massachusetts, is inside glass, right? Inside windows, because that's where a lot of the heat's leaving from your house. And so if we could take this great thermal insulator, aerogel, and stick it in between the two window panes, like we have in here, and I can prove to you that there's aerogel because you can kind of see the light that gets scattered, the pathway of the laser going through the aerogel. So this does in fact have aerogel in it, and it's kind of a higher density aerogel, so it's not quite transparent because it's Oh, okay. So anyway, you got this translucent material, but you could imagine perhaps getting like more transparent aerogel, kind of like this one, and it's not perfect, but again, it lets the light through, but it doesn't let the infrared through, and can trap heat really well, and it would do a lot to decrease energy costs in our homes and in our schools and stuff like that if we could have some sort of way to keep the energy in so we don't waste the energy.
So on that same topic, aerogel is used in some commercial products, maybe not things you're familiar with, but it's used predominantly as an insulator. And so as we start to go to more extreme environments, either just to explore them or to look for energy resources, we need materials that will help us there. And so the military has developed what's called an ultra-warm sleeping bag, which is actually, you don't sleep in aerogel, but in between those materials there, you've got an aerogel-based composite. So that it really works well in low temperature environments. There's also a company that makes something called toasty soles, which is an insole for extreme environments. And this woman actually climbed Mount Everest with toasty soles, and she has some testimonial that her feet felt as warm if she was on the beach in Hawaii or something like that. I don't, I'll leave that for you to interpret. And then for maybe a more, as we explore for energy in more harsh environments, in cold environments, northern Alberta and whatnot, for example, is one example. There's a market now for insulation for oil pipelines, because in those environments you really, as it gets very cold, the oil can congeal and can clog up your line, and then you have all kinds of problems. If you want a really good thermal insulator to try to prevent that from happening. So I'm wrapping up here in the next couple slides, and I wanted to talk about, actually, I guess a little more esoteric use of aerogel. Actually, people have used it as an artistic medium as far as sculpturing, making sculptures and whatnot. And this guy is an artist from Greece who actually, he uses the fact that the gel will conform to whatever, when it's still a sol, right? It's still a liquid, so we could pour it into a mold. And so he designs molds of various things he wants to sculpt. and then supercritically extracts them and makes these structures, which are kind of fun to look at. So as an extreme material, let's talk about an extreme environment. Space, that's where aerogel is seen. It's gotten most of its interest. I'll talk about this in a second on dust collection, but it's used currently on the Mars rover as thermal insulation, as well as use in spacesuits. I'm not sure it's actually fielded in spacesuits right now, but they've studied it. So let's talk about stardust for a second. You might be familiar with this. I believe there have been Science on Saturdays that talk about it, talk about all the implications of it. I'm just going to talk a little bit about the material. Stardust really proved that aerogel is a real good medium for interstellar dust collection. So this was launched in '99, came back in 06, and so it was a comet flyby. It flew by the Wild 2 comet and put out this panel that had aerogel cells on it to collect dust from outer space. And this is when they first unloaded it. These are the aerogel cells that they unloaded. And then when they went through and looked at them, and one of the reasons they needed aerogel is, you couldn't use just a piece of plastic to stick up and have these parts, because the comet's moving fast, the probe's moving fast. And so if they collide like that, your particle might vaporize. It might just get so hot. So what they had was aerogel that would give a little bit. And so you see the impact crater where this first part comes in, and then actually you can see it's kind of slow catch. It was a soft catch. You can see that you can particle track down to these particles, which then they analyzed and looked at for various implications in astronomy. So I'll wrap up here. I had this question. This slide wasn't in the first presentation, but I had this question a lot about, so we've talked about silica aerogels, but the structure of aerogels can be applied to a lot of different other elements. And so here's a periodic table, and we've looked at a number of different materials, been able to make a number of different aerogel-based materials that might be useful for other applications, but I got that question quite a bit, so I threw this slide in based on that. As far as applications at Livermore, one of the primary ones is development for targets for our National Ignition Facility. So they would be maybe utilized as targets for the NIF laser to focus down on and look at high energy density physics experiments there. As well as looking at with the high surface area as a catalyst for potentially fuel cell materials. I mentioned hydrogen storage in energetic compositions, as well as precursors for making ceramics. So instead of having a low density thing, we've got a high density material that's actually transparent also. So if you learned a couple things today, Mr. Reese and I will be really happy. I'll kind of skim over them again. We learned what an aerogel is and how to make it and what it looks like on the outside and on the inside. And we talked about what surface area is and its importance. We spent some time on density, which is an important concept for any material. One of the first things anybody asks about a material is, well, what's its density? And so density, of course, is this ratio of mass to volume. And then we looked at different ways thermal transfer works, through conduction, which is through the solid, convection, which we would call through fluid, and radiation, which I would say through light. So I'd like to thank you guys all for your attention, and Mr. Reese and I would be happy to answer any questions you guys have. Thanks.